All right, good afternoon, everybody. So in the last lecture, we were talking about strings. And in particular, we were looking at the scanf, or the scanf function. So scanf is the function that will scan a string and parse data from the string, storing the result in variables that you specify. One of the important things to remember about scanf is that many of the conversions will ignore leading whitespace. So here we've got a string with two spaces in it. Whitespace also includes tabs and new lines. So here we have a string with two spaces in it, and our conversion specifier here is %s, %u, %s. So %s and %u, both these conversion specifiers will ignore leading whitespace. So when scanf processes this string, it will read the ABC and store that in string 1. It stops reading ABC because it comes to a space. So the %s specifier, the other thing to remember about the %s specifier is that it stops when it encounters whitespace. So the first conversion stops there. The second conversion ignores that space there, sees the 1, and then sees the space so that it knows only to convert the 1. So the 1 gets stored in x1. Then the next conversion ignores that space there, reads the rest of the string xyz, gets to the end of the string, so it knows to stop, stores xyz in string 2. Right? And this ignoring of leading whitespace works or occurs when you read in floating point values or integer values as well. So here, scanf reads in the -99, stores it in y1. Here it is. So the string, the formatting string has a space after the %d. So it ignores all trailing whitespace in this case, right? Looks for the comma, finds the comma, so that's good. Right? The space here means ignore all leading whitespace, but you don't actually need that because the %f conversion is going to ignore all leading whitespace anyway, and then reads in the -1.5, stores that in z1. And so that's the way it behaves. Now the problem occurs when you want to read in a string that includes whitespace. So if you want to read in a string and you want to keep the whitespace, what do you do? And so you have a couple of options here. One option is to use the square bracket conversion. So %opening square bracket lets you match any specified set of characters. Right? So %square bracket and then some set of characters will match any non-empty string made up of characters in the set. So for example, %square bracket ABC will match any string made up of the characters A, B, or C. Right? It'll stop reading the string once it finds a character that is not A, B, or C. Right? And so a space can be one of your characters. The caret in front of the set means match all non-empty strings that do not include characters in that set. Right? So notice there is a similarity here to how string matching works in Bash. Right? It doesn't work the exact same way, so you have to remember that as well. Right? This is C, it's not Bash. The matching is not going to work in exactly the same way. So here it's not ABC, so this will match any string that does not include A, B, or C. This conversion does not discard whitespace before attempting a match. It considers whitespace to be significant. The problem with this, not the problem. One of the features of this conversion is that something like that is not guaranteed to work in C. So the language says there's no portable way to define a range of characters, right? And in Bash, you can define a range of characters, and it almost always works the way you want it to. So that thing there may not match all strings made up of lowercase English letters. Right? For example, it may match only strings made up of the letter A, hyphen, or Z. Right? It depends on your operating system and on your, I guess mostly it depends on your operating system. Right? So if you want to match all letters, the portable way to do it is to list out all the letters that you want to match. Right? So A, B, C, D, D, all the way through Z. There's no way to specify character classes either, right? So this, using the POSIX character classes, that's a bash regular expression thing, right? Not a C square bracket conversion. All right, so this conversion is useful when you are trying to extract information from a delimited string. So a delimited string is a string where there are special characters that mark fields in the string. And so this one, this example here, I'm going to try to extract information from a string where there is a comma separating the elements or separating the fields of the string. So here I've got Bart Simpson and some made-up student number here. Right. I'm going to try to read in the last name, the first name, and the student number. Right. So there's many ways you could do this. Right. So for example, you could read in. There's many ways you could do this. I'm going to do this with the square bracket conversion. Right. So I know that my delimiter is a comma. So what I can do is I can read in everything that's not a comma first, right? And that will read in the last name. Right. So the way you read in everything that's not a comma is to use caret comma, right, inside the square brackets. Right. Then you want to match a comma, so that's part of my formatting string. Right. Then I have everything that's not a comma, so that'll read in the first name. Then I have the comma, and then I have the %u, so the student number at the end. Right. And so if this works successfully, you'll get 3 conversions, right? One for the last name, one for the first name, one for the student number. Right. So here I've got some error checking here, right? So if n's not equal to 3, then we fail to extract all 3 fields. Exit is a function that you can use in C to stop the program. So it exits from the program, and it sets the exit status to whatever value this is. Exit failure is a constant that is defined as part of the standard library. I don't know what its actual value is. I suspect it's 1, but it's some non-zero value. If we do get 3 conversions, we're just going to print out the fields that we got. Right? So here we got Bart Simpson, student numbers 1, 2, 3, 4, 5, 6, which is correct. Right? If you, will this always work? Yes, this will always work. So even if you have a space in the name, right? So notice that consumes the space. So yes, it reads the space as being significant, right? Anything that's not a comma includes the space. Right? This should always work, assuming you have all 3 fields, right? If you have an empty field, it's going to fail to extract all 3 fields, right? So this conversion will always result in at least 1 character being consumed if it succeeds. Right? This one fails because there's nothing at the beginning of the string. That is not a comma. All right, so along the %n specifier is another conversion that doesn't actually produce. It produces the number of characters that have been consumed so far. It does not result in an extra conversion. So the value that's returned by scanf does not go up by 1 if you use %n. Right, and so it is occasionally useful to know when did this conversion, how many characters have been read after something has been consumed in the string. Right. So in the previous example, right, it might be useful to know, right, what is the index of that comma and what is the index of that comma. Right? You can get that index if you know that 1, 2, 3, 4, 5, 6, 7 characters were consumed when you're reading in the last name, right? Because that comma is going to be at index 7, right? And then if you know that 4 more characters are consumed when you read in the second comma, right? That'll also be useful. So that'll be a total of 11 characters consumed, right? That could also be useful because that is the index of the second comma. So if you want to know how many characters have been consumed after a conversion has occurred, right, you can use %n. And you can use this as many times as you like in the formatting string. Right? And you can put it wherever you want as well. Right? So here's an example. It's the exact same example. This time I'm going to create 2 extra variables. Right? And these will be the indexes of the first and second comma. So to parse the string, I'm going to use the exact same conversion, except I'm going to insert a %n here, right? So everything that's not a comma, right? %n then tells you how many characters have been consumed so far. So the first conversion gets stored in the last name, right? The percent %n gets stored in I1, right? Then there's the comma. So this is the comma between the first and last name, right? Then this is the first name, and that's the number of characters that have been consumed so far after reading the first name, right? So it's not 4 in this case, right? It's the total number of characters that have been consumed. Then there's the comma between the first name and the student number, and then there's the student number, right? And so I2 is going to be stored. I2 will hold the index of the second comma after reading in the first name, right? So that and that, right? Even though you have to specify variables in which to store them in, they don't count as conversions, right? So that %n does not contribute to the returned value, right? Here the return value should still be 3 if you read in the first name, last name, and student number successfully, right? So assuming I do read in all that information successfully, I now have the indexes of the commas, so I can go into the original string, right? And at index I1, I can replace the comma with some other character. So here I'm replacing it with the vertical bar, right? And if you run that example there, right, you now get that output there, right? And so I've just modified the original string so that the commas have now been replaced with vertical bars. And there's lots of other use cases for knowing how many characters have been consumed after a conversion, right? So for example, you might try to read in an int value from some file somewhere, right? And if you and then you can see how many characters were consumed after reading in the int, right? So if you consumed 1 character, you know the int value is between 0 and 9, for example, right? If you read in 2, you know it's somewhere between -9 and 99, right? And so on and so on and so on, right? So there's lots of use cases for knowing how many characters have been consumed. All right, so those are the conversions. Those are the conversions that you should know about. Don't memorize these for the purposes of a test, right? So again, on the exam, you do get an appendix that describes. It doesn't describe all of the conversions, right? It describes the ones that I think will be useful for the test questions. But don't go ahead and try to commit these to memory. It gets worse because now there are some optional modifiers that you can also use, right? So if you want to, when you're reading a string, you might decide, look, I'm going to read in all these parts of the string, but I only care about certain parts, right? So in other words, I don't want to store the result of parsing one of the fields in a variable because I don't need it, right? But I still need to do the conversion to make sure that the string is being read in correctly. Right, so if you want to suppress assignment, you can use a star modifier. Where does it go? The star goes in after the %sign. Right, so if you use the star modifier, the conversion still happens, but the assignment to the receiving variable does not happen. Right, so that's all it does. So here's the exact same example again. Right, notice in the previous example, I never actually used the last name, first name, and student number. Right, all I wanted was the indexes of the commas so that I can go into the original string and replace them. Right, so if that's all that I want, if all I want are the indexes, right, then I don't have to assign I don't have to remember the last name, the first name, and the student number. Right, so here when I read in the last name, I use a star before the conversion, right, and this says read in everything that's not a comma, and then discard whatever was read in. Right, so I'm not going to store it anywhere. Right? Then give me the number of characters that were read. Right? Then consume a comma. Right? Then read in anything that's not a comma, discarding the result. Right? Then give me the total number of characters that have been read so far. Right? Then read in a comma, and then read in an unsigned int, again discarding the value of the unsigned int. Right? So here I only have 2 receiving variables. Right? Notice I've also commented out the int n. Right? So in this case, the only possible value for n is 0 because no receiving arguments are ever assigned. Right? That's not assigned anywhere. Right? That's not assigned anywhere. That's not assigned anywhere. %n does not contribute to the return value. Right? So the only thing this thing can possibly return is 0. And then you go ahead and replace the commas with vertical bars in this case. Right? So this is occasionally useful when you are reading something and you only need part of the thing. So you're reading an entire string, but you only need parts of the string. You don't need to extract all. You don't care about all of the individual pieces of information. All right, another optional modifier. This one is, I would say, less optional because this is sometimes important. So you can restrict the number of characters that are read when a conversion is performed, right? So when you're printing something, if you do something like %4u, right, that says use at least 4 characters to output the result. Right? When you're reading something, it's at most 4 characters when you're reading in the result. Right? So here %4u means consume at no more than 4. It's going to mean digits here because it's the %u conversion, so unsigned int. Right? So try to convert this thing as an unsigned int, consuming no more than 4 characters, or no more than 4 digits in this case. Right? So the no more than is important because, especially when you're reading in strings, right? Because when you're reading into a string variable, your string, your array that you're writing into has a fixed length, which hopefully you know, right? And you want to make sure that you don't read more than that, more characters than you can store in that variable, in that array, right? And so when you're reading strings, you're often also specifying the maximum field width. Here I'm not reading into a string. I'm reading in digits, right? So here I can say to read in the date, make sure that the year has no more than 4 digits, the day has no more than 2, and the month has no more than 2, and the day has no more than 2. Right? It doesn't say you have to read in 4. It doesn't say you have to read in 2. Right? It says no more than. Right? So if this thing works, we should get 2023 129. Right? I guess if we go many, many, many years into the future, right, we can see what happens. So in the year 12,023, right, I told the conversion to only consume 4 characters, so now we get 1202. Right, %4u. So read in no more than 4, right? Then there should be a hyphen. So after reading 4 characters, there's now a 3, right? So now the conversion stops. So scanf stops. It says the string that you're reading doesn't match what you told me I should be getting, right? And so the conversion stops there, and it leaves the 3 in the string, right? So it doesn't consume the 3. Okay, so this is, there is a line here, right? So using the maximum field width modifier is of particular importance when you're reading in strings, right? And you want to make sure, because especially when you're reading in data from an untrusted source, right? You want to make sure that there is space in your array to hold the characters of the string, right? And so you typically are going to specify the maximum number of characters to consume. Here's another one. This is Apu from The Simpsons, right? Who has a very long last name. Right? So here I've only allocated 10 characters for the last name, right? 9, in fact, because you need the null terminator, right? That last name contains many more than 9 characters, right? So when you run this example, right, now you get the error message, right? Failed to extract all 3 fields, right? I can't read that entire last name. I don't have room for it, right? So here I'm reading in at most 9 characters that are not a comma, right? So it reads in the first 9 characters of Apu's last name. I don't know if that's 9, but anyway, right? And that's as many characters as it will try to read. Right? It then tells you how many characters were read, and then looks for a comma. Right? So I guess we should count here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So that's not a comma. So now scanf stops and says returns only 1 conversion was successfully completed. Okay, so the %C conversion is the conversion that will read in characters, right? So normally when you use %C on its own, reads in 1 character, right? If you specify a maximum field width of W, then %WC will match exactly 12 characters, including white space, right? So %C is another way that you can use to read in a string that contains white space. So that means the receiving argument must be an array of char of capacity at least equal to W. Now you have to be careful with %C. Right? %S always reads in a string. Right? It always stores the null terminator into your receiving argument. %C never stores the null terminator into the receiving argument. Right? So if you do this, right, you say I need to read in a string. It contains a character. I'm going to use contains a space. Sorry, I'm going to use %C with a width with a maximum field width. You have to remember to append the new line or the null terminator into the array yourself. Right? So in other words, you have to make sure that number one, your array has at least W plus one has room for at least W plus one characters. Right? And then you have to write in the null terminator yourself. Right? So this one's the next example uses scanf with %C to extract data from a string. Right? The first use finds lengths of 2 comma-separated strings, right? And then we're going to dynamically allocate some arrays to hold the strings. So we're going to jump ahead a little bit to show you how to read this thing in properly. All right, so here's a string. This one's hard-coded into the main function, right? But you can imagine that you're reading in a file, right? When you read in a file, instead of scanf, it's fscanf, right? And the function works exactly the same way, right? So when you're reading in a file, you don't know how long that line is going to be, right? So one of the problems you have when you're reading in stuff from a file is you have to figure out how long is this last name. Right? And so what I'm going to do first is I'm going to use scanf and figure out how long is the first name. Right? So I'm going to throw away or not assign the read in last name anywhere. Right? I'm just going to read it in. Right? So read in everything that's not a comma. Right? Don't assign the result anywhere. Right? Then remember how many characters have been read so far. Right? And I'm going to store that in I1. Right? And now repeat, right? So now look for the comma, right? Read in the first name, so everything that's not a comma, throw away the result, right? And then how many characters have you read so far? Right? Then look for the comma and then read in the student number, right? So because I have the values I1 and I2, right, I now know the length of the two strings, right? So the length of string 1 is going to be I1, right? I read in that many characters for the last name. So I can now make an array of length 1 plus 1. Right? And you'll see probably in about 15 minutes or so, one way that you can dynamically allocate an array is to use this function called malloc. So malloc is one of C's dynamic memory allocation functions. Right? It'll try to grab you a chunk of memory that is at least that big. Right? So in terms of numbers of characters. Right? And I can now treat that as an array. Right? So I can now store the last name in last name. Right? How long is the second string? Well, I have the indexes of the two commas. So I can do I2 minus I1. Right? And then if you're careful, right, you subtract 1, and that gives you the correct length of the last name, of the first name, sorry. Right? And then I can go ahead and allocate an array big enough to hold the first name. Right. Now, I can generate the correct formatting string. Right. This is actually quite an involved example, right? So to use scanf, I need a formatting string. So there's my array to hold the formatting string. Right. I know it's not going to be very long, right? I have to read in a string of some length, followed by a comma, followed by a string of some length, followed by an unsigned int. Right? So that's certainly going to take less than 100 characters. Right? So I need to write in the percent. I need to write in the percent sign. Right? So to write in the percent sign, right? So in the formatting string, remember the percent sign is significant. Right? So to write in a literal percent sign, it turns out there's a conversion specifier in printf. Right? So when you're using printf, if you use %%, that tells printf to write a percent sign instead. So write a percent sign. Right. %zu is the conversion for it is the correct conversion for size t. Right. and length 1 and length 2 are of type size t. Right? So %ZU is going to be my conversion, right? And then followed by a C, right? So because I'm reading in characters, right? So this says %, right? Whatever the value of length 1 is, right? Format it as an unsigned int, as a size t object, right? Followed by a C. Right. So for this example here, it's going to be %, however many characters are in the last name, plus 1, followed by a C. Right. Then followed by the comma, followed by %, followed by the value of length 2, whatever that is, followed by a C. Right. And I can now read in the first name and last name using scanf, right? So now with scanf, I can read in the original data string, right? Using my newly computed formatting string, storing the last name and the first name, like that, right? So if you run this, right, it actually does successfully read out the information from the string. Right? And there you can see, so that it was the formatting string that we computed back here. So there's a nice little example that uses both sprintf to write a formatting string, right, and then scanf to read a string where we don't necessarily know how long the fields are that we're trying to read in. Right? I guess Apu's last name has 17 characters in it. I guess it's 18, right? 18 in this case. Yep, 18. Right. Okay. Now, the only, I guess here, so here I just created, when I computed the formatting string, I just made a string that was really long, right? So 100 characters long, more than enough room to store that formatting string, right? More than enough room to store that, for example, right? So it's less as an exercise for the student to determine how to reliably determine the theoretical maximum capacity required for the formatting string, right? So notice that someone has asked this, right? So if I have to compute a formatting string, how long do I make the formatting string, right? So if you want to click on that link there, you can see Stack Overflow's answer or answers to this question here. All right, let's see. Oh, yes. Size of the receiving argument. All right, so if you've really, really been paying attention, you might have noticed that there's one conversion for base 10 integers. Right, so %d will do base 10 conversion, right? But there are multiple integer types that might be used for the receiving argument, right? So one thing that will convert all integers, right? But you can store the result in different variable types, right? So you might store it in an int, you might store it in a long, you might store it in an unsigned, in a signed long value, right? Or in a short value, or in something else. So there's one more modifier that you should be aware of, and that lets the programmer specify the precise type of the receiving argument. Right? This only matters if you're dealing with overflow and saturation effects. Right? And furthermore, it gets pretty hairy, so this notebook doesn't try to cover everything here. Okay, so there's a commonly used, so when you're trying to read in double values, the receiving argument type, you should use %lf instead of %f. Right? If you're trying to read in long integer values, you're going to use ld instead of just plain old d. Right? And another example is size t. So size t, in previous versions of the language, so I think before C99, there was no conversion for size t. I don't even know what year or what standard size the conversion for size t came in at, right? So you would just read it as %u. But the preferred way to read in a size t value is with %zu. Right. All right, so here is an integer value, right? So that's 3 billion, which is bigger than int max on my computer. So on my computer, int max is roughly 2.2 billion. Right? So if I read this with %d, right, that says, read it in as an integer, right? If I try to store that in an integer value, right, it is unclear what's going to happen here. Right? Will I get overflow? Will I get an error? Will something else happen? Who knows? Right? Because that value here, or will I only get the first 8 digits? So will I get 300 million instead? Right? So not clear. If I read it into a long value, though, 3 billion certainly fits inside long. Right? That is a billion, right? Sorry, I just want to. Yes, that is a billion. Okay, so that certainly fits within the range of long, at least on my computer. Right? So if I read it with %LD, right, that tells scanf, convert this as a long value, a long integer value, right? This should work. So let's see what happens. Okay, so here when I print out I, so remember I is the int value read in by scanf, right? And j is the long value read in by scanf, right? Notice that the int value, it seems to have overflowed. Right, which is actually not surprising. That's probably what most people would expect would happen. Right? J correctly stores the value 3 billion. Right. Here's an example with reading in floating point values. So that's 10 times 1 times 10 to the 100, right? Which is bigger than float max on my computer, but it's less than double max. Right? So here, when I read it in with %f, right, and store the result in a float, I'm probably going to expect this thing to saturate, so it's probably going to hit positive infinity. If I store it in a double, though, it should work correctly. Notice when you print the result, right, so this is one of the annoying things between printf and the scanf family of functions, right? There's inconsistency in how it treats the conversion specifiers, right? So for scanf, right, if I read in a double, I should read it in as %lf, but when I print it, you always print it as %f, right? There is no %lf when you print. That's what that comment is there for. So what happens here? So yes, so that's exactly what happens, right? So when I read in the value into a float, right, it saturates and you get positive infinity. When you read in the value into a double, it works correctly. Why did it print it like that? %f, %d. That's surprising. Oh no, that's the way it should print it out. Never mind. Sorry. Yes. So it does print out the value correct. It prints out the value. You'll have to take my word for it. That is the correct floating point value. Right. All right. Okay. So what happens with scanf when you do something like this? Right. So if I try to read in a value that doesn't fit in the range of float, right? What happens exactly? So the standard says behavior is undefined, right? So on my computer, I get saturation and overflow, right? But on someone else's computer or some other operating system or some other compiler, right, you may get a completely different result. Right? So just keep that in mind when you're doing these conversions with scanf, right? You may have to specify an additional argument, an additional modifier to specify more fully the type of the receiving argument. All right, so that's it for the string notebook. There's a lot of information there, which is why it's a very long notebook. Any questions on strings? Or the string standard library, or the standard library functions that work with strings? All right. So the next topic in the course is another thing that should be new for most of you, assuming you haven't programmed in C or C++ before. And so this is the dynamic memory allocation notebook. All right, so in C, if you have a variable that has automatic storage, right, the variable lives for, the lifetime of the variable is the point at which it was declared to the end of the block in which it was declared in. So if you're in a function somewhere and you make an array, right, that array only lives for the length of time that that function is running. Right? When the function returns, that array no longer exists. So there's no way that you can write a function that returns an array that has automatic storage duration, right? So that returns an array. I don't know if I brought my pen. I did not, right? That you declare by writing int square bracket x, for example, right? Or int 12x, or sorry, int x square bracket 12, right? You can't return that array from the function because that array doesn't live anymore once the function returns. Right? So if you want to return something like an array or any object from a function, right? Or if you need that object to persist across multiple function calls, right? You have to manage the memory for that thing yourself, right? And so so those types of objects fall under or have what's called allocated storage duration, right? In allocated storage duration, the programmer controls the lifetime of the object, right? And so if you've only programmed in Python or Java, this is a completely alien concept, right? Because those languages, you create the object, and then when you don't use it anymore, you don't care, right? It goes away eventually on its own. So in C, if you want to make an object where you're managing its lifetime, there's a bunch of things you have to do, right? So step number 1, right? Your object occupies memory somewhere. You have to ask for enough memory for that object, right? So that's what's called dynamic memory allocation, right? Once you get that chunk of memory, you don't have an object yet. You've just got a raw chunk of memory, which again is another thing that's very alien to Python and Java programmers, right? Python and Java, you're always calling new, or in Python, you are calling a constructor, right? And that constructor runs and creates or fills in, ensures that the memory that's being occupied has a valid object in it, right? In C, it's your job to do that, right? So once you've got your chunk of memory, you have to go in and fill in all the memory that you need, all the values that you need to define that object, right? Now that you've got a chunk of memory with an object in it, you go ahead and use it, right? So you use the object for as long as you need, right? And then when you're done with it, number 1, you have to determine that you're done with it, right? Once you've determined that you're done with it, you now have to free the memory that was allocated to that object, right? Because if you don't, the memory that was allocated for that object never gets returned to the operating system until your program ends, right? And so if you forget to deallocate memory for your objects and you're making lots and lots and lots of objects all the time, right, eventually your process will run out of memory. And then your program will probably crash. Right? So in C, it's the programmer's responsibility to deallocate any resources that are used by the object. Right? And so this notebook is concerned mainly with memory, right? But there are other resources that your object might require. Right? If your object requires other resources, right, you have to release those resources as well when you're done with the object. Right? An example of this is files. So to open a file in C, you need what's called a file handle. Right? When you're done with the file handle, you have to return it back to the operating system. Otherwise, it's possible that your operating system can no longer open up any other files. Right? Okay, so for memory, there are 3 functions you need to know about. They're all called more or less the same thing. Right? They're all variations on alloc. Right? So malloc, calloc, and realloc. Each one of those functions tries to allocate a block of memory of a specified size, returns a pointer to the to the start of that memory, to the beginning location of that memory. And then you can use that pointer to do whatever you want with that chunk of memory. Right? When you're done with the chunk of memory returned by one of these functions, right, you free that memory by passing in the pointer that you got when you called malloc, calloc, or realloc. So newer versions of C actually have 3 more functions. There might be more that I don't know about, right? We don't care about these in this course, right? And you probably wouldn't care about them. Most programmers probably don't need to know about these or wouldn't use these on any regular basis. Right. Okay, so malloc. Malloc's the function you'll be using probably the most. The other one will be realloc. Right. So malloc allocates a block of memory. Right? That's all it does. Right? The memory is completely uninitialized. Right? So wherever malloc got that memory from, right? If that memory has already been used for something, right? It's got a bunch of bits in it that are not zeros and that are not all zeros. Right? The return chunk of memory, they'll still have whatever values were there. the last time that memory was used. Right? So this is completely uninitialized memory. It returns a pointer to the block of memory that was allocated for you. Right? If malloc fails, right, in principle it returns null. Right? So it tells you, hey, I couldn't get a chunk of memory. In Linux, malloc never fails. So in other words, it always returns a valid pointer. And so we'll talk more about that shortly. Right? Size is the number of bytes of memory, right? So the number of multiples of car that you want. Right? So if you want a single car, you just pass in 1. Right? If you want 2 cars, you pass in 2. Right? If you want an int, you pass in size of int. Right? You want 2 ints, you pass in 2 times size of int, and so on and so on and so forth. Right? You are allowed to pass in 0, but the standard says you must not use the pointer for anything if you pass in 0. Right? In C, there are no 0-sized blocks of memory. Right? So the smallest array you can have has 1 thing in it. So you should avoid passing in 0 to malloc. If you look online, a lot of people, a lot of advice will cast this pointer to the pointer type that you want. Right? So for example, suppose you wanted to allocate an array of int. Right? So you're going to store that in a pointer to int. Right? A lot of online resources will cast this return value to int star. Right? You do not have to cast this thing to int star. Right? And most authorities will tell you not to cast it to int star. Right? So don't cast the return value, just store it in a pointer of whatever type you need. Okay, so here's an example of using malloc. Several examples of using malloc. Right. Okay, so malloc 1 gives you back a pointer to a chunk of memory that can store 1 car. Right? So I can store that chunk of memory in a pointer to car. Right? So in this case, right, so here, right, so if you just write car star C semicolon, right, you don't have a car object. Right? There's no, like C is not pointing at anything. When you write this, right, C is now pointing at a chunk of memory where you can safely store a car. Right? So now you can dereference C and store whatever value you want in the memory pointed at by C. Right? So star C equals A means store the character A in the chunk of memory that C is pointing at. Right? Does that work? It absolutely works. You can print out the value of the object that C is pointing at. Right? So again, dereference C, right? That's a car, right? And you can print out that value. Right? So C points at an A, so that works correctly. Right? Okay, so here, the lifetime of the object being pointed at, right, starts here, right? So immediately after this line, C is pointing at a car object. I am now under control of the lifetime of this object because I'm using malloc to allocate memory for it. Right? When I'm done with the car object, I have to get rid of it. So here, immediately after I print it, I get rid of the thing that C is pointing at. Right? So the lifetime of C now ends there. Right? This is just a trivial example, right? You would never do this sort of thing in a real program. But this is just emphasizing the fact that I am now under control of the lifetime of the object. Right? And I'm just going to do the same thing over and over and over again. Right? If you want an int, or one dynamically allocated int, right? How much memory do you need? Well, I need size of int memory. Right? So call malloc with size of int, and you can store that in a pointer to an int. Right? You now have a valid int object. Right? You don't know what its value is, but it's valid. Right? Whatever memory I is pointing at, that's your value. Right? So I should probably go ahead and assign a sensible value to that memory. So I'm going to write 99 into that int, right? And then I can print it as well, right? So dereference I to get the int object being pointed at, print the int. Then I'm going to be done with I, so I'm going to free it right away. Again, you wouldn't do this in real life, right? So there's 99, right? Not surprisingly, you can do the exact same thing with a double, right? So allocate one size of double, a chunk of memory that can hold one double value. Right? I'm going to store the value minus 1.5 in there. Right? When I print it out, right, I get minus 1.5. Right? And now what about structures? Right? So for a structure, right, there's my 0.2 struct up here. Right? You can do the exact same with a structure, right? Structure is no different than any other object in C. So if I want to allocate one point 2 object, right, I just malloc size of struct point 2, and that gives me enough memory to store a point 2 object. So remember, this gives you back a pointer, right? It doesn't give you back a struct 2 object, a struct point 2 object. It gives you a pointer to one, right? So if I want to go in and fill in the x and y values of that point, right, I'm going to use the arrow operator here to access the member, so dereference the pointer and access the member in one shot. Right? Again, you could write star s inside brackets and then write dot x if you like. Right? The arrow operator is easier. Right? And you can see here when we print out the structure, we get back a structure whose coordinates are 0.5 and minus 9.9. Right? And again, of course, free the allocated memory when we're done with it. If you want an array, right, just multiply by n, the size of memory by n, where n is the size of your array. Right. So here, n is going to be 8. Right. I'm going to make right. So here I malloc 8 bytes of memory. Right. So I can store a string of length 7 in that array. Right. So C is not an array. So I guess that's the thing to do. C does not point at an array. Right? It points at a chunk of memory that is 8 cars long. Right? You can just treat it as an array if you want to. Right? There's nothing stopping you from treating it as an array. You can treat it as anything else if you wanted to. Right? In C, we'll let you cast this pointer to something else. Right? You can cast it to a double, and you could store a double value in the chunk of memory that was returned. Right? Here, I'm going to treat it like it was an array. Right? And so I can copy the string sys220 into the chunk of memory that C is pointing at, right? And this will work just fine. Right? So that prints out sys220. Right? Suppose I want an array of 3 ints. Call malloc, pass in 3 times size of int, and you now have a chunk of memory that can hold 3 ints. Right? You can treat that. You can treat I, right, as being a pointer to the first element of the, you can treat, so I is just a pointer to the first int in the array, right? So writing I0 means set the first element of I to 1, right? I1 means set the second element of I to 10, and I2 means set the second element of I to 100, right? And that also works just fine, right? So there are your 3 elements stored in I. You can do the same thing for double. You can do the same thing for structures. Right? So here I've got an array of 3 doubles. Right? And I'm going to store -1, -10, and -100 in that array. Right? Here is an array of 3 3.2 objects. Right? I'm going to store 3 separate points in that array. Right? And when I print that out, that also works exactly the way you want it to. Right? Okay, so you now know how do you write a function that returns an array, right? Well, you use malloc. Right? So this function here returns an int array, right, of a specified length. Right? Length is size t, so it's unsigned, right? So it's 0 or greater. Right. I know that in C, I'm not allowed to call malloc with, if I call malloc with 0, I can't use the return pointer for anything. So if someone passes in 0, I'm going to set length to 1. Right. This will let me safely return the returned pointer, and somebody can treat the array as an array of length 1. Allocate an array. Oh, wait, that's buggy. No. Length times size of int. Right? If I just write length, I get an array of car. I get enough room for length cars. Right? I want length ints. So you have to multiply by size of int here. Right? I write in -99 into the first element just for illustration purposes. You wouldn't do this normally. Right? So that allocates an array of length 10. Right? So when whoa, what happened? Thank you. There we go. right? And so the first element in A is minus 99. If you were to print out the other 9 elements, you don't know what you can't expect to get anything in particular, right? Here you probably get zeros, you may not, right? But you do have a total of 10 ints in that array, right? I have to stop there. It's 20 after the hour, right? Yeah, so that's a good place to stop, actually. Okay, so I guess we'll continue this lecture on Monday of next week.